Coming here again. This is L George Academy, and today we're going to be looking at some questions to prepare students for exams. So some of the questions we'll be dealing with some likely questions in physics. Now let's start with linear expansivity. For linear expansivity, a table, we have to remember that linear expansivity itself, linear expansivity is the increase in length per unit length per degree rise in temperature. So a question can come like this. Okay, let's see linear expansivity, we use alpha to represent it. Alpha equals to increase in length per unit length per degree rise in temperature. This is the increase in the length, this is the unit length, the original length, and this is the temperature rise. Then making this subject formula, we have L2 minus L1 equals to alpha L1 delta theta. Then we take this L1 to this side, we have L2 equals to L1 plus alpha L1 delta theta. Bringing this together, we have L1 into 1 plus alpha delta theta. So this is what we call, this is the formula for linear expansivity. Let me use a marker for you. Linear expansivity. This is the formula for increase in length or change in length. Increase in length. Then this is the formula for the new length. New length. So we have to note these three formulas when you're solving linear expansivity. A question can come like this and say that what is meant by the linear expansivity of copper? The linear expansivity of copper is 0.00017 per Kelvin. Remember that per Kelvin is the unit, SI unit of linear expansivity. It's 0.00017 per Kelvin. It means that copper will increase by 0.00017 units for every degree rise. For every degree rise in temperature. Or we can say copper will increase by 0.0017 units for every 1 Kelvin rise in temperature. So this is a simple question that one can see from here. Now, we also note that there is also linear expansivity. We have linear expansivity alpha. There's another one we call area expansivity. This has to do with area. So area expansivity is represented with beta. And beta, this is defined as the increase in area per unit area per degree rise in temperature. Cross multiplying, you have A2 minus A1 equals to beta A1 delta theta, and bringing A2 to the A1 to this side, we have A1 plus beta of A1 delta theta. Now, factorizing A1 out, we have A1 into 1 plus beta delta theta. So this is the formula for area expansivity, or another name for it is superficial expansivity. So then this area expansivity, we also have this is the change in area. Change in area. This is the formula for change in area, and this is the formula for new area. So, and you have to know the conversion for, if you are told to convert, let's just look at some of these simple conversions, because you may have questions on conversion. If you are told to convert 10 centimeters square to meter squared, 10 centimeters square to meter square, you want to convert it to meter square. This is the volume in centimeter. No, this is the area in centimeter, and you want to convert it to area in meter square. Of course, you know that everything you do in physics, most times the SI unit of length or anything of this kind is always in meter. So we have to change it to meter square. So now how do we do that? 10 centimeter means we are talking about 10 times 10 raised per minus 2. Centi is 10 raised per minus 2 meters. So if I say 10 centimeters squared, is like saying 10 times 10 raised per minus 2 squared meter squared. That's the meaning. So, and that will give us 10 raised per minus 4 meter squared. This is, we have a 10 here. Sorry, the square is only for this. That's centimeter squared. So you have something like of this nature there. Okay, that's not what we are really talking about. Now, a question can be asked that prove that beta equals to 2 alpha. In this kind of question, the thing we need to do here is to start from the first. So we have to note that B equals to A2 minus A1 over A1 delta theta. And we also know that A2 equals to A1 1 plus beta delta theta. We already know this. But we want to prove that this beta equals to alpha. You recall that L2 equals to L1 plus L1 into bracket 1 plus alpha delta theta. Before I even recall this, you can say that A2 is the same thing as L2 B2. If A1, since A1 is L1 B1, so we have set A1 as L1 B1, then A2 as L2 B2. So for L2, we have given this. Since this is a length, then we can also imply that B2 will be what? B1 into 1 plus alpha delta theta. Then you bring this into this equation. Because we are having A2. We are looking for A2 equals to A1. What is A1? L1 B1. So now A2 is what we are looking for. A2 is L2 B2. So we want to compare it. Now L2 B2, we are bringing this equation, these two equations. Let's call this one equation star star. Bring these two, put star and star into this, into A. Then we have A2 equals to L2 L1 into 1 plus alpha delta theta times B1 into 1 plus alpha delta theta. Now multiply, open the bracket, we have L1 B1 into 1 plus alpha delta theta all squared. Now, if we open this using binomial expansion, we have L1 B1 into 1 plus 1 squared plus 2 alpha delta theta plus alpha squared delta theta squared. Now we know, look at alpha. Alpha for copper is given to us as 0.000017. This is very small. It's a very small amount. If I now say alpha squared, it will be giving me 0.00000 in 8 places of zeros before 17. That's a very negligible amount. So therefore, we state that what? Since alpha is small, alpha square is very small and negligible. So we are neglecting the alpha square from this equation. So this one tends to 0. That part tends to 0. So we can write A2 is equals to L1 B1 into 1 plus 2 alpha delta theta. And from here, we can see that A2 equals to L1 B1. L1 B1 is, from our equation here, L1, B1 is A1. A1, then 1 plus 2 alpha delta theta. This is our required equation. Let's call it equation gamma. Now, for this, if you compare this with equation, let's call this equation, the original equation we have, equation alpha. I'm comparing this equation alpha with equation gamma. You will see that A2 is A2, A1, okay, let's write this, A1 equals 1 plus beta delta theta. We can see that A2 is A2, A1, 1 plus theta, then beta equals 2. Therefore, beta is 2 alpha. Quite easily done. We have been able to prove that beta equals to 2 alpha. That is a simple question that you may also see in now let's look at this question, a table given to us, and we are given that the original length, we have the original length given to us as 500. The table says 5 original volume V1 equals to 500 meter cube, and the linear expansivity was also given to us. The linear expansivity is 18, but in the table we have 18, then times 10 raised power minus 6 per Kelvin. Now for this table, okay, this one is meter square, millimeter square. This is millimeter square. That's original area, because the unit tells us if it is area or so. Original area is given as that. Linear expansivity is given to us as the linear expansivity. Let's write it as 18 times 10 raised to minus 6 per Kelvin, and we are looking for rise in temperature in, that's the E part. This page 56 of your new school physics has this question in tabular form. So we are looking for the E, which is the rise in temperature. The rise in temperature, that's theta. Then we also have the increase in area length. So for this to be change in A, increase in area. So change in A was given to us as 0.36 millimeter squared. Now, this is a question on area expansivity, and for the question we are looking for delta theta. We remember that alpha equals to change in, sorry, we are dealing with beta now. Beta equals to 2 alpha. So we need to multiply this 2 times 18 times 10 raised to minus 6 per Kelvin. So beta is equals to 36 times 10 raised to minus 6 per Kelvin. So that's our beta. You have to convert it. Since you are dealing with area, you have to look for the beta. So far, you have been given the alpha. So now the next thing for us is that we need to write our formula. Beta equals to change in area over area, original area, delta theta. I want to make delta theta the subject formula. So bring delta theta to this side. Delta theta equals to delta A over A1 beta. So what is delta A? Delta A is 0.36 over 36 times 10 raised to power minus 6 times A1 is 500. So in this case, we have delta theta. Without using any calculator, I can change this and say this is 36 times 10 raised to power minus 2, 1, 2. So that's 36 times 10 raised to power minus 2 over 36 times 5 times 10 raised to power minus 6. Then there is a tiny, okay, let me take it small, 10 raised to power 2. So by indices, we have this is as 36, we cancel 36. So we have 1 times 10 raised power minus 2. Bring this up. You have times 10 raised power 6. This becomes plus, and this becomes minus when it comes up. Times 10 raised power minus 2 over 5. Now, this is minus 2. When we add it, it becomes minus 4. Minus 6 minus 4 gives us, so that theta here equals to 1 times 10 raised power 2. Do we understand? So then divided by 5. Divided by 5. So 1 divided by 5 gives us a 0.2, and times 10 raised power 2. In this case, when you add it, this will give you 20 Kelvin. And that's how to solve that question. That's how to solve that question. Okay. 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 So now that's that about sorry for the break in transmission. There was a power outage, so we need to look out for that. Then we also have a question also on aluminous expansion of water. We need to also understand that when we talk about aluminous expansion of water, under expansivity or expansion of liquids, we discussed anomalous expansion of water, and we said that water, all other liquids expand. All other liquids expand when heated and contract on cooling. But water, in its own case, has a kind of anomalous behavior, an abnormal behavior. Anomalous means an abnormal kind of behavior. Now, other liquids, let's look at, well, I'll use a graph to do this. Let's say water is starting from minus 10 degrees. This is 0 degrees. This is 4 degrees. This is 50 degrees. And this is 100 degrees. This is a graph of volume against temperature. If you are to explain anomalous expansion of water, you should understand that other liquids do expand this way. From a lower temperature, they just go straight and keep on expanding. This is for other liquids. But in the case of water, water starts from, let's say, minus 10. It keeps on expanding until it reaches the 0 degrees Celsius. At 0 degrees Celsius, between 0 degrees Celsius and 4, there is a contraction. And between 4 degrees Celsius and 200, there is also an expansion rate. So it keeps on expanding. So a question can come here and tell you that the lowest, water has the lowest volume at 4 degrees Celsius. So water has the lowest volume at 4 degrees Celsius. And if you're going to draw it at density against temperature, it is the other way around. You have minus 10, 0, 4, 50, and 100. For density against temperature, there is a decline in the, and it first starts contracting from that -10 and expand until it reaches 4 degrees Celsius. Then from 4 degrees Celsius upwards, it contracts back. So this question can come this way, that water has highest density and lowest volume at 4 degrees Celsius. So the temperature where anomalous behavior of water is observed is always between 0 to 4 degrees Celsius. That is the temperature at which anomalous behavior is observed. Okay, so also let's look at, I'm trying to look for some questions that can help us to understand this. Okay, so then let's look at, I'm just going through different areas. Stay on heat and expansion. So when we look at application of convection current in nature, one of the most prominent application that we have is the land and sea breeze, and which is a consequence or a result of the convection current in nature. Now we know that during the day, let me draw the diagram first. During the day, let's have this as the sun, and this is the land, this is the water body, this is the land, this is the sea. During the day, the land gets heated up quickly, more quickly than the sea, because the land is a better absorber of heat than the sea, and the land also has a lower heat capacity, a lower specific heat capacity. That means it will take, it just needs a small amount of energy, to get heated up. Are you getting it? So it has a lower specific heat capacity, but is a better absorber because it does not need much heat before it gets heated up. So this makes the air around the land to be warmer, and air that is warm is less dense, so it will rise up. So warm air rises up from the land. Warm air rises up from the land, and as it rises up from the land, cool air from the sea, replaces it. And this cool air from the sea is what we call sea breeze. So the sea breeze is a kind of air that moves from the sea towards the land. So it is a cool breeze that moves towards the land during the day. But at night, this is still the land, and this is our water body, the sea, this is the land. At night, the reverse is the case. So you have what? At night, I said the reverse process takes place, and you see that because this land has a lower specific heat capacity, it loses most of the heat before night time, but the sea still retains most of it because of its high specific heat capacity. That of water is about 4,200 joule per kilogram per Kelvin, so it's very high. So it still retains some of the heat, and that makes the air around the sea to be warm. So warm air rises up from the sea, and cool air from the land comes to replace the ones that have risen up. So this cool air or cool breeze from the land towards the sea is called land breeze. So this explanation on convection currents in nature, land and sea breeze. Also, we can also look at application of heat, application of conduction. You have your cooking pot. That's why it's made of what? Metal. And the type of metal is aluminum, because aluminum has what? Higher thermal conductivity than iron or than some other metals. So it has higher thermal conductivity. If you use a steel, you'll get the result faster because it has higher conductivity than that. So let's look at application of when you look at the area of thermos flask. The thermos flask this is the cork support. This is the cork. This is the cork stopper. This is the double silvered wall, silvered glass wall. Then we also have the vacuum. We have the cork support. And we have the casing too. We have the lid cover. So then they ask you that draw a thermos flask, and explain how it is minimized. And explain how it is minimized in this particular material. Now, the first thing is the cork stopper helps to reduce heat loss by the liquid there, by evaporation and by convection. The cork stopper helps to reduce heat loss by evaporation and convection. The double silvered wall glass helps to reduce heat loss by conduction. The vacuum helps to reduce by conduction. That's why it's not touching. So if this was touching this, there will be conduction there and it will be lost. But the vacuum helps us to reduce heat loss by conduction. But the silver wall glass helps us to reduce heat loss by radiation. It radiates heat. Heat coming from outside will be radiated back. Heat coming from inside will be kept inside. So the silver glass wall helps to minimize heat loss by radiation. Also, the cork support also helps to reduce heat loss by conduction, because if it was touching the metal casing, there will be heat loss to the surrounding. So this application of this is a thermos flask. So it's a kind of flask that keeps whatever is kept in it warm or cold. I think we have another episode of this very soon. See you in the next class. Have we ended this end?